Training a modern neural network requires millions of matrix multiplications to execution every second across thousands of processing cores. The velocity of these calculations makes the learning process difficult to observe in real time. Before 2015, debugging these networks relied on primitive programmatic outputs. Researchers printed loss metrics directly to terminal consoles, providing a stream of numbers, but no historical context or trend analysis. Standard plotting libraries required engineers to halt the training loop to render visual artifacts. This forced a choice between seeing the data and actually processing it, as generating a graph physically interrupted the computational flow. Treating machine learning observability like standard software diagnostics crippled hardware utilization. The math ran too fast for traditional logging to capture, without bottlenecking the research itself. Extracting high-dimensional telemetry without starving the GPU creates a massive performance conflict. Resolving it requires physically separating the producer, the training script, from the consumer interface. Observation must not introduce latency. The communication remains strictly one way, ensuring diagnostic rendering never blocks the GPU's matrix multiplications. TensorBoard enables this through strict asynchronous architectural decoupling. By separating the metric logging mechanism from the visualization server, it moves the heavy lifting of data processing away from the training loop. This creates a specialized, out-of-band distributed observability system. The graphical interface is the final layer of a pipeline designed specifically to stay out of the way of the hardware. The pipeline begins at the instrumentation layer. As the model trains, the framework acts as the producer, capturing scalar metrics, gradients, and weight histograms at predefined step intervals. Standard ACID-compliant relational databases are too slow for this ingestion. Their reliance on transactional locks creates contention, inducing latency that would drag down the speed of the training script. Instead, TensorBoard uses a dedicated background file writer thread. This thread asynchronously serializes data into highly structured protocol buffers, a language-neutral, binary format designed for efficient serialization. Bypassing traditional database architectures entirely ensures that writing diagnostic data never interrupts the GPU's critical execution path. These protocol buffers flow to an intermediary storage layer, binary.tf events files located on the local file system. The format is strictly append-only. The system writes new data exclusively to the end of the file, enabling lock-free writes that prevent I/O bottlenecks. But machine learning scripts are frequently preempted in cloud environments. Sudden process terminations often leave I/O writes incomplete, threatening to ruin the entire log. TensorBoard addresses this with cyclic redundancy check, or CRC, framing. Each data block is wrapped in precise checksums, allowing the parser to detect a broken frame, discard it, and continue reading subsequent valid events. This framing ensures a 10 GB log file remains viable even if a crash corrupts the final bytes written to disk. On the consumer side, a standalone backend process continuously pulls the local directory for new data. In modern environments, this is handled by Rustboard, a high-throughput server written in Rust. A model training over millions of steps generates an insurmountable volume of scalar data. Attempting to load every single telemetry point into RAM would trigger an out-of-memory crash on the local machine. TensorBoard manages this through reservoir sampling. The system maintains a fixed size buffer for each tracked metric, regardless of how long the model trains. As the stream of data arrives, the algorithm probabilistically decides to keep new points or discard older ones. This maintains a uniform, statistically representative sampling of the entire training curve, while keeping the memory footprint static. This architectural trade-off sacrifices micro-level data fidelity to guarantee that the user maintains macro-level observability over the entire experiment. This decoupled architecture also handles structural introspection. The Graph Explorer parses the model's static node topologies, mapping thousands of operations into a zoomable, hierarchical UI. The system expands into hardware profiling by hooking into underlying APIs, like the NVIDIA CUDA profiling tools interface. It tracks execution times for individual operations across the GPU. This tracing visualizes host-to-device memory transfer delays. It exposes exactly when the GPU sits idle, starved for data because the CPU preprocessing pipeline is too slow. Pinpointing these bottlenecks allows systems engineers to optimize their data loaders, recovering hundreds of engineering hours and significantly reducing cloud compute costs. This local, file system-based design is less suited for the modern era of large language model agents, where prompt tracing and tool use evaluation require cloud-native, distributed tracking. In 2026, TensorFlow 2.21 officially removed TensorBoard as a required dependency. This decoupling eliminated long-standing version conflicts and allowed the toolkit to evolve independently. This shift positions TensorBoard as an essential profiling engine for edge AI. It provides the diagnostic depth needed to monitor quantized models compressed for mobile hardware via runtimes like LiteRT. Localized low-latency tools are mandatory for debugging networks that operate without constant cloud connectivity. Developers rely on this depth to ensure accuracy survives the transition from high-power servers to mobile NPUs. The architecture of TensorBoard leaves a definitive legacy. How the data moves through the system dictates exactly what we are able to see.